from one-way continuous slab. Now, one-way continuous slabs, we are two types of problems. One which we can solve by using IS code method, and second we have to go by basic method, that is moment distribution method, and then we will get final moment and then reinforcement. Now in case of one-way continuous slab, we have seen, so we require minimum 3 spans, and smallest span should be within 15% of largest span, and this criteria satisfied for this problem, because highest is 3.4, and if we will go for 0.15, then that will be less than 3 meter. So it is within our both the criteria, and we are not going for any redistribution, so that criteria also satisfied, so we can use IS code method. Now spans we have given S1 3 meter, S2 3.2 meter, S3 3.4 meter, S4 3.1 meter. Now width of the support is given to 30 millimeters. Floor finish is 2 kilonewton per meter square. Live load 4 kilonewton per meter square. We have M25 and FE 500, and also we have to draw reinforcement details. So now we will first effective spans. So as per IS 456, our width of support we have less than clear span by 12. So we have to use two criteria as per 22.2, that is center to center distance and clear span plus effective depth. So first we will go with center to center distance, because we do not know effective span, effective depth, and therefore center to center distance maximum we have to consider for trial depth, and therefore we will go for 3400 plus 230, and that will give me center to center distance, which will be 3630 millimeter. Then we will go for trial depth. Now we have continuous slab, so our basic L effective by D we have 26. Into modification factor we will assume 1.35, so percentage still 0.3, and then from this we are going to get effective depth, which will be 103.42 millimeters. So now knowing effective depth, we will add effective cover 20 millimeter, as we are in slabs, so effective cover is generally taken as 20 millimeters. From this we are going to assume, or we are going to provide overall depth 130 millimeters. So if we will subtract effective cover minus 20, so it will be 110 millimeters. Now we have effective span, and that will be equal to clear span plus D, and that is equal to 3.4 plus 0.11, and that will gives me 3.51 meters. The effective span is minimum of 1 and 2. So 1 we have seen, that is 3.63 meters, and 2 we have 3.51 meters. So we have 3.51 meters. That is effective span S3. Now S1, S2 and S4 we can find by using clear span plus effective depth, because effective depth is less than the width of support, and we will get first as 3.11 meter, second 3.31 meter, third we know that is 3.51, and fourth we have 3.21 meters. Now then we have load calculation. So we have total load, dead load plus live load. Dead load is self weight of slab plus floor finish. Self weight we have 25 D. We have overall depth 0.13 meters, that is 130 millimeters, so 3.25 kilonewton per meter square. Floor finish is given, so this is given actually. So we have floor finish, so we need not require to assume this. This is given. And then we have floor finish 2, and then we have given live load, that is imposed load is also given, which is 4 kilonewton per meter square. Now dead load we have total, that is 3.25 plus 2, that is 5.25, and WUD, that is factor dead load 7.88 kilonewton per meter square. Slab we have, so we have assumed 1 meter width. Live load we have 4 kilonewton per meter square given, so we have WUL 1.5 into 4, 6 kilonewton per meter square. Then we have bending moment calculations. Now as we are using IS code method, so for bending moment we are going to use bending moment coefficient that are given in table 12. So you can see this table 12 where we have bending moment coefficients. Now we have alpha D, that is 1 by 12, 1 by 16, that is for span moment, for dead load, and for live load we have 1 by 12 and 1 by 10 and 1 by 12. Now we have formula of mu alpha d WDL square plus alpha L WL square. Now WUD we have seen we have 7.3 per meter, WUL we have 6 kilonewton per meter square. So now if you will see the coefficients for dead load, so you can see we have near middle of a end span. So we have this as end span, we have this end span. So values we have 1 by 12 here, we have 1 by 12 here. And then we have at middle of interior span. So for both these, we have 1 by 16, 1 by 16. If we will go for imposed load, so you can see for near middle of end span, so we have on both sides 1 by 10, 1 by 10, which is given over here, 1 by 10. And then we have 1 by 12, which will be at middle of interior span, which is this 1 by 12. And then using this, so we are in position to calculate values of mu1, mu2, mu3, and mu4. Now this is S1's effective span 3.11, S2 3.31, S3 3.51, and S4 3.21. So we have bending moment 12.15 kilonewton meter, 10.92, 12.23, and 12.95. Now this maximum we have 12.95 kilonewton meter. Now we have shown over here that is in short. So we have these values. So we have total bending moment that is likewise. So we have to put it in this fashion. Then we have that is for support moments. So we can see alpha d. We have at support next to end support minus 1 by 10, and at other interior support we have minus 1 by 12, which is alpha d value, that is for dead load. And while live load, you can see we have minus 1 by 9 everywhere. So formula we have same again. So WUD same, WL same. And then we can have this dead load minus 1 by 10. You can see at support next to end support. And this value we have minus 1 by 10. So next to end support minus 1 by 10. And at interior support minus 1 by 12 for dead load. And for live load, we have, that is imposed load, we have minus 1 by 9 everywhere. Then we are going to calculate this value. Now the change you can see over here. So we have to take average value of the moment. So as our load is same, so we are going to consider average span. So first we have 3.11, second we have 3.31. So average we can take, it will come 3.21 square. Similarly, if we will go for next support, then we have 3.31 and 3.51. So it will come 3.41, which will be average. And in third, we have 3.51 and 3.21. If we will go average, you have 3.36 square. So we have these values, and we have maximum bending moment 16.43 kilonewton meter. As it is at support, we are saying it minus. Now we have to go for the depth for 16.43 maximum moment. So in the same way, we have prepared this. So we have this will be total moment. So now depth from bending moment consideration. So we have to take Fy 500 is given. So Ku max 0.46, FCK 25, Ru max we will get 3.34, and from this we will get depth required 70.14. We have provided 110, so it's okay. Then we have reinforcement. So we will go for maximum value of mu reinforcement, and other we can only tabulate. So we have this will be maximum bending moment. We have 16.43, and effective depth we have 110. And from this we are going to get value of AST required. So this is maximum moment already we have seen, and we have this AST required becomes 368.18 mm square. AST minimum we have 0.12%. B into capital D we have to keep in mind, and from this we will get this value that will be 156 millimeter square, which is less than 368 millimeter square. And therefore we have to use maximum of the two. So we have to go 368.18 mm square. So spacing, we are going to use 10 mm diameter. So maximum allowable diameter we have 16.25 as per IS code, and that is greater than 10. So 10 mm it's okay. Now a small AST, that is area of 1 bar, which we are going to provide and we have that as 10 millimeters. So we have area 78.54 mm square. So spacing we have 1000 into small AST upon capital AST, which will be 213.32 millimeters, which is less than 300 mm and 3D. So now, so provide 10 mm diameter bars at 210 millimeter center to center. And therefore, from this AST provided, we have 374 mm square. So this we have to keep in mind, which is greater than AST required. So you can see, so similarly, we are in position to find out AST required. Now AST for span moment is less, though we will go for 8 millimeter diameter bars. So spacing you can see in bracket you will get as required. So against 267, we require 188 spacing. We have provided 180 and AST provided for this 279.25. Against 238.69, spacing required is 210.59. We have provided 210, and against this AST provided becomes 239.36. Similarly, for 268 and 285, these values are given over here. So maximum value of reinforcement provided in span moment is 295.68. Now 3.11, so this is for your span moment at support. So now again in the same way required is 333.67, for which spacing required is 235, and these are the provided 230 spacing and 341.48, that is area of steel. So maximum we have provided area of steel as 374 millimeters square. Then we have distribution reinforcement, which will be minimum, and that is 156 mm square, which we have already seen. So we are going to use 8 mm diameter bars, gives us 322.27 millimeter, less than 350 and 5D. So we will provide 8 mm at 320 mm center to center. Now check for deflection. AST provided, we are going to consider maximum, that is 374, and that we will use us 0.34. Maximum we are taking so that the modification factor we will get less, and from this we will get modification factor 1.35. So D required we have 100 millimeter, provided is 110, so it's okay. So check for deflection is satisfied. Now maximum shear force, so we are taking 50% curtailment and 50% we are going to be continuing the support. So steel available at support is only 50% provided. Now we have seen that now we will go for shear force, calculate shear force. So maximum shear force we are interested. VU, we have formula alpha D WUDL plus alpha L WUL. WUD we know, WL we know. Now these are given. If you will go to this, then you have this value. That is for shear coefficients. 0.4 we have at end support, 0.6 at support next to end support, and at all other interior we have 0.5. So in the same fashion we have taken these values. If you will now see, so 0.4 at end support, 0.6 and 0.55, that is next to end support, and 0.5 at interior support, that is for dead load. And for live load they have given the values, that is 0.45, 0.6, 0.6, 0.6, and same we have taken, that you can see now. So from this VDL, due to dead load we have these values, and for live load 0.45 and other values we have, that is 0.6. And from this we are going to get, that is total VU, maximum value we have 27.85 kilonewton. So we have to check against this value, that our capacity of shear or resistance to shear. So we are now going to be steel at support available. We have 0.5 into 295.68. This we have taken, that is at end, because we are interested at support that VU value. So now we have 147.84 millimeter. Now from table 40.2.1.1, K value is 1.3, which we require for VUC, K tau CBD. Now we will have percentage PT 0.13, and this is less than 0.15%. Therefore, tau C is taken as 0.28. And then we are going to get this value as 40.04. So this value we have actually 40.04. So this is wrong one. So 40.04 kilonewton, which is greater than 27.85. We have taken actually larger, but though we have considered this is at end supports. Then development length. So we have VU 18.79 kilonewton mu we have seen, this is we have at support again, and that value we have taken, maximum value we have 12.95, and against there we have shear force 18.79, just also we have seen. And then from this we are going to get value of m1 6.48 kilonewton meter, because 50% we are assuming steel is available, so resistance we have half of this. So LD, we have this formula from which we will calculate development length required. Now we have this formula, and by using only 1.3 m1 upon vu, our requirement is satisfied. So we need not require to go for L naught, that is any hook, any hook. We need not require to go for any hook in this one. So hook will require, any hook will require if your value of 1.3 m1 by vu is less than this LD. And therefore we have 448.32, which is greater than 388.39, which is our requirement. So L naught, this is not required over here. And so this satisfies our development length check. So now you can see the steel. So we have 8 mm 180, and 50% we have curtailed. So 180 we have, that is till center of supports, and 50% curtail, which will give you us 360 millimeter center to center. Now from where we have to curtail, so 0.15 L. So 0.15 into L, we have to take 3110, that is L effective in this, and that comes 470. Now from this we know that is 0.25 into 3110. So that comes 780, that we have rounded up these values. Now you can see these values we have calculated from center. So we should be very careful when we will talk about curtailment on bottom side, that will be from center. Then similarly for second span, here we have span that is 3.21 meter. And then accordingly we have to calculate 0.25 gives us 830, and this 0.25 same we are going to get. Then we will go, so remaining also you can provide, I have not shown all these spans. Then we have, this will be 0.1 L. Now when we will talk about top reinforcement, it should be from support, from face of the support. So 0.1 L, so we have 3110, so into 0.1, so 311, so we have provided 320 millimeters. So this we have to provide from face of the support. Now similarly we can have these values from face of the support. Now, so we should be very careful with this. So now this will be 0.15. On this side we have 0.15 into 3110. On this side 0.15 into, we have, that is 310. So accordingly we have calculated these values. So 0.15 L, and alternately we have to go for 0.3 L. So you can have these values. Actually these all reinforcement which I have shown, this is above the second one, but actually these all reinforcement are at same level, top also and bottom also. Though I have shown this below, but this is at same level. And similarly I can have here, that is 0.15 L, and alternately we have that is 0.3 L. So likewise we have to show the reinforcement, that is at top and bottom. So this is all about your one-way continuous slab. So thank you. So today we will stop here only.